Did everybody make it in? No, everyone did not make it in. Who's gone today? Wesley's gone today. Jason's just in the restroom. Everybody else made it. Okay. Joe, glad you're back. Ariman, glad you're back. But now Wesley's gone. Okay. As you guys are peeking at homework, how would you do the first section? Oh, homework went away. Sorry. What are they asking? Pass the terms. How do we show that two vectors are equivalent? What did you find in your notes to help you with that? Yeah. Do you see it? Nope, we have to go back. Just like, magnitude. So how long? And then direction. And what did we use yesterday to find magnitude? What theorem is this, technically? Pythagorean. And it was super easy if you're starting from the origin, but what extra step did you have to do if you were starting somewhere else to do Pythagorean? The distance formula, or just think change in x, change in y. So Pythagorean theorem, super easy if we're from the origin, if we're from 0, 0, because you go over and up to your point. But if you're somewhere else, you have to think of how far over, how far up, or the distance formula to get the magnitude. But then direction, what did we use? Once we figured out how far over, how far up for each one, what were we able to make? A triangle. And what were we looking for? An angle whose opposite and whose adjacent. Whose opposite and whose adjacent were given. So magnitude needs to match, direction needs to match. Now, that's first section. What's second section of homework? Component form. Hey, is there an example in notes like that? Wasn't it the next example? What were the directions in notes? Find the component form and the magnitude, right? So component form. What did I call these guys yesterday? They were like brackets. They're like parentheses, but I technically call them side. Oh, what do you call them in English? No? Do you guys not use them as a proofreading? It's a caret. Yeah, it's called a caret. Anyway, awkward. When you're editing papers, technically you're supposed to use carets for, what's the actual term? I should know this, but it's been a while. Like if you leave out a word, but there's a snazzy way of saying it. That's okay. It's been a long time since I did editing. But anyway, you would use a caret for some sort of missing word. That's like a normal caret. It's like an upside, or we use it in math also for powers, right? The caret on your calculator raises it to an exponent. But this is a side caret. But it's like parentheses, it's like brackets. But my question to you is the following. Does this stand for a point? No. It doesn't stand for a point. It actually stands for movement. What's the first number stand for? How far? Why am I going to say left? Because it's an x and it's negative. Good. So the first one's going to say how far left. I'm moving 3 to the left from the initial point. And then what's the second one stand for? 2, and specifically 2 up because it's a positive. So remember, when you're doing components, you have to actually think of when you're given an initial point and a terminal point, which way do we subtract again? Initial minus terminal or terminal minus initial? T minus S, right? Terminal minus initial. So the ending point, wherever the arrow is, minus the beginning point, wherever the first point was. So then you can subtract. Component form, side carets. Doing subtraction of the x's and subtraction of the y's. And then magnitude. Oh, yeah. How do you do magnitude again? You can just do Pythagorean. Yeah, and the reason we can do it so simply is because we've already figured out what the a and b is just by doing our subtraction. So component form is super nice because you already know your a and b. You don't have to do a big old nasty distance formula like we did before we found our a's and our b's. So when you have components, it makes the notation just a little bit easier. So find the component and find the magnitude using subtraction first for components and using the Pythagorean second for magnitude. That's second section. Oh, keep going. Oh, keep going. Okay, what's the third section? But what's happening to the vectors? They're being added, multiplied, added and multiplied and subtracted and multiplied. What does that look like? Well, kind of, but isn't it just sort of where we ended yesterday? We were just starting to say what happens when you multiply. Oh, hey, we did one of these. And instead of going this far, how far did it go? That far. We doubled the x and we doubled the y. So what would you do, for instance, when you saw or when you see in homework? The very first one, I think, multiplies. Oh, but what does it multiply by? We talked about it yesterday. What happens if you multiply a vector by a negative? That's it. Because the length doesn't change, right? It's -1. The length doesn't change. But all that you need to change for this one is just v going the opposite way for number 25. You could just do, if you wanted, one graph. It's going to get a little messy, though. You could do one graph and then color code, kind of like we did with transformations a while ago. Or you could just do a quick sketch every time. But this guy says take vector v and just have him go the opposite way. But we were just starting to do plus and minus, and that's where we ran out of time. So we're right here in homework. We're in the 20s, and we're right here in notes. Let's figure out what happens in the picture when we add. Yesterday I said what happened in the math. The math is easy. If you have components, how far up from beginning to end of v, how far over, how far up from beginning to end of v. It's as easy as put the x's together, put the y's together. Technically, put the change in x's together, put the change in y's together. But how does that work when we have a picture? Let me go ahead and give you an example of u and v. Didn't we yesterday say that v could be -3, 3? So let's use that again for this guy. Let me zoom in just a little bit. So what if, once again, v was -3, 3? But let's try to figure out what u could be based on that. So v could be -3, 3, going left 3, up 3. So let's do that again. 1, 2, 3. And then going up 1, 2, 3. What does u look like then? It'd be left, right? Equals. So u goes left 1, so -1. What do you guys think? Going down 1 or down 2?
2.
I guess we can kind of budget and make it 2, huh? All right, we'll make it 2-ish. So down 2. Mathematically speaking, it's pretty easy. What's u plus v? Add the change in x's, add the change in y's. So what's -3 plus -1 going to be? Or, if you want to do it the proper way, -1 plus -3. Just add them, guys. What's -2 plus 3 going to be?
2 plus 3, 1.
What am I doing? Adding. Why am I adding? Because they told me to. Okay. We're just adding. We're okay, right? I have 2 people adding. We're in pre-calculus. Are we okay? Tell me good morning. Say hi. Something or others. Use your voice. Are we okay? Okay. Now, I know they're negatives. I know they're not everybody's favorite, but hold on. We're in pre-cal. We can do negative numbers if we put our mind to it, right? But right here they did, Matthew. So what's -3 plus -1? Got it. What's -2 plus 3? Got it. That's true. Good point. Matthew's getting you guys ready for homework where they didn't give you numbers, but let's use the numbers to try to figure out how the pictures work. That's what I said a little second ago. -4, 1. What would that do in our picture? What's the answer? 1, 2, 3, -4. And then +1. What Matthew just warned us of is in the homework, they don't give you numbers for that one little baby section. Sound like help her out. A little quick tap on the shoulder. You're good. Coming back. If this is the answer, and in homework there's no numbers, homework again if you want. How am I supposed to know how far left, how far up, how far down, how far? Wait, pause. Do you guys remember how we can move vectors? And do you remember how in the roller coaster, really precise picture, we needed to flow through and do the steps in progression? Not separately, but together? Pick it up and move it. Where does this guy come from apart from the numbers? From the progression of the vectors. From the progression of the vectors. Does it make sense? Right now, if I tell you to turn left on Woodley, yeah, you can do that, right? You could turn left on Woodley. But what if I told you right now, no, I need you to turn right on Chatsworth? That's Woodley. I can't turn right on Chatsworth. What are you talking about? But what if I tell you to turn left on Woodley and then right on Chatsworth? Would that make sense? The student parking lot, okay, maybe I should talk about Kinsey, but whatever. If you're coming out and you were looking at Woodley, if I told you to take a left on Woodley, you could do that and then take a right on Chatsworth. As long as you pay attention to street signs, you could eventually do that. But if I right out here said turn right on Chatsworth, you're like, but I don't know how to get there. Some of you would. Most of you probably wouldn't. So coming back. Separate vectors working against each other don't make sense if I'm trying to put them together unless I put them in a progression and say, do this and then do that. Oh, hey, look. Then it makes sense. So in homework, when you see u plus v, should you connect those two? No. What do I need them to do? First one, then the other. What do you guys think you could do to add u plus v in the homework problem for number 27? Move, yeah, I would say move. Move who?
U over to the right.
You could move u over to the right, but just to get you ready for u minus v, remember addition you can do either way, but subtraction can you do either way? So technically, if we're doing u plus v, just to make it super proper, I'm actually not going to move u. I'm going to say u and then, okay, so who am I going to move? V. U and then v. Does that look about right? I guess it's a little bit off. But we could try to make it about right. Does that look about parallel? A little bit better. U and then v. And what did you guys see in the picture? What happened or what was the addition? It wasn't just the u plus the v, it was the overall result. So what's the answer to u plus v? Technically, it's going to be that little guy, who is the connection of going u and then going v. I'll have you guys ponder homework a little bit more, but let's do a few more examples, because we need to talk about not just adding, not just multiplying, but what happens when you kind of put it all together. Let's see if we have another example up here. So we could go ahead and label, and I'm sorry I didn't label. This guy would be our 2v. That's this whole vector from beginning to end. And then our u plus v is this guy right here. What happens when you put the two together? Now technically, Jason, you were totally following me, which was awesome. But what I did was v plus u, which is actually okay in addition. Just in subtraction, that could get us in trouble, because we can't just flip the order. So what if we have an example? I want you guys to do the math, okay? Just the math. We'll deal with the pictures in a second down here. We'll deal with the pictures in just a second. But for right now, if you have the components of u to be 2, 1, the components of v to be 1, 3, you can't do bold in your notes. What should you be doing over u and v? Over every single one in your homework too when you're writing your directions. Don't make me write a million different notes on all of your Google Classroom assignments to write the arrows above. It's not very fun for me. Vector u, vector v, just with the numbers. What would you guys do for a and b and c down below if you had to get the components of the sum of the difference of, well, ready, set, go. Go. We will soon, but let's do the numbers first. Because this one has numbers, unlike the ones in the beginning of homework and, well, the beginning of this concept in homework. Shouldn't take you too long. Hopefully it should just make sense. But pause, turn to people in your group, just see if you're starting to match up. Let her see, you might have to double check your work. It takes a couple steps to get there. Pause and collaborate, just at least with A and B. How you doing? All right, my stubborn ones, collaborate. Let me hear you talking real quick. Check your answers. Be like, hey, how's it going? What'd you get on? Go. Is anybody wondering, is it really that easy? Good. That's exactly what you should be thinking, because the answers, P.S., I sketched him. If they don't tell us where to start, I say whatever. I'll start from 0, 0. It's easy. Right 2, up 1. Right 1, up 3. Just getting ready. Just getting ready. But the numbers were easy, because you just have to do 2 plus 1 is 3. And 1 plus 3 is 4. Done. Numbers are easy. Right? Good. 2 minus 1, 1. 1 minus 3, negative 2. We weren't scared of that negative, right? Bless you, bless you. All right, this one a little bit harder. Did anybody actually think of 2u when you're like, oh, hey, okay, 2u would be 4, 2, right? That's okay, as long as you thought about it. I'm just double checking our mental math real fast. 3v would be 3, 9, right? So then 4 minus 3, good. Good. Dun, 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 math. Go team. But now it's time for the graphs. But the math, are we okay? All right, Lauren, I don't want to steal it. Put it away, kiddo. So 3, 4, 1, negative 2, 1, negative 7, like the easiest thing of the entire year in pre-calculus. But how do you do the graphs? The first one said u plus v. Okay, so what if we have u? What if we have v? Which one's which? U is blue, right? Okay. So who am I going to move if I'm actually going to go in order as far as what they want? Do I start with U or start with V? So start with blue, and I'm going to go blue, but then what do I want to do? Backtrack and then go green? No. I want to go blue and then go green. I need to unconnect all my pieces. I have to still unconnect all my pieces. They're too connected. There we go. How does that match up with what I need it to be? What's 3, 4? Can't you graph it? Can't you go ahead and say, oh, okay, go 1, go 2, go 3, and then go 1 and 2 and 3 and 4? If you go 3 and if you go 4, where have you gotten to?
3, 4.
So one way to graph is actually just to say, oh, 3, 4, done. The other way to graph is to say, go U, go V, and then connect. Both ways work, and both ways get you the final answer. So let's try that on the second one, because on the second one, it might get even a little harder to do it, because we haven't done a minus yet, at least not in the graph. So instead of starting with the picture, instead of starting with U and V, let's start with the answer, because you guys just found it, and it was easy. So what are the components of my U minus V? 1, negative 2. So take a second and graph 1, negative 2 as a vector from the origin. So going 1 and going negative 2. This is about what I got. You guys agree?
Yep.
Okay. So 1, negative 2, going right 1 and down 2. But how does that make sense with the picture? We go U, and then what do we do with V? We go U. No, not adding V, because that ends us here. Subtract it, but what does subtracting do? What we need to do is flip V first. if I can actually get him there. And then add. If I can actually get it. There we go. So instead of going U and then a positive V, U in the way V normally goes, I'm going to go U and then opposite V. I'm going to go U and then the other direction of V. But once again, you could have just started with the answer, 1, -2, if you have the numbers, right, Matthew? If you don't have the numbers, you have to think about, ooh, I need to flip V and then put it, and now I should be able to connect. So remember, in each of these, the red one is the final answer of the sketch. All right, time for the last one. We can graph the final answer. It's easy. Right? You guys tell me how to graph. I'm going to go 1 to the right, and I'm going to go down 7. Okay. Now, hold on. This is up 3. So I'm going to go down 3, down another 3, and then down another 1. So I think 7 is going to be about there. So it's going to be 1 and 2 and 3 and 4 and 5 and 6, about. So I'm going to guess that one a little bit more than 1. I'm going to guess it's about there. Now how can I match it up? How many U's am I supposed to go? 2 U. All right, so let's take the U. And let's double them. All right, how many V's am I supposed to go? 3. So 1, 2, 3. But what's supposed to happen to all those 3 V's? It's negative, so what does that mean? Uh-oh, undo. Oh, I lost them all. I forgot my shortcut. Sorry, guys. There we go. What am I supposed to do with them all? Oh, I lost one. Poor little guy. Now what? How close did I get? Pretty close. Not perfect. I know, not perfect. But it was pretty close because I was estimating. But does the 1, -7, end up matching the 2U minus 3V? Yeah. Does that kind of make sense? And why am I showing you this again? What does homework have you do for one baby little section? Use graphs only to figure out the results. Use graphs only to figure out. Why is that a little hard? Well, I don't remember. Pause. Could you pretend these are numbers?
Yeah.
What do you guys think? -2, 1? Kind of looks like it, right? -2, 1. Could you make it like 2 and, I don't know, maybe like a 4? So you could pretend what they are if you wanted to. You can make little numbers with vectors. Or you could try to use the ideas that I just did in notes to try to help you and at least estimate what each of the different results might be. I keep on saying results because in math, putting all of these together with vector diagrams gets you what is called a resultant vector, the overall result. All right, hopefully that'll help you in that section of homework. Ah, what's next? Hey, are we going to mind this section? Why not? All you have to do is just put them together, and then, oh, you have to sketch it. But wait, hold on. If you have the numbers, did we technically have to do the whole, like, flowing through? Or could we just, like, jump there? Just jump there. That's okay. Okay, so what's next? Oh, unit vector. We learned something about him yesterday. What did we learn about a unit vector yesterday? A unit vector has a magnitude, Matthew just said it, but most of you probably didn't hear it, of 1. Well, how do I make it have a length of 1 if it doesn't already? Let's see if notes are going to help us out, and the answer is, well, Is this warning us of anything? Kind of tells us a lot of properties. Do any of these properties not make sense to you? U plus V is V plus U, okay. U plus 0 is, okay. I think we already know most of these, yeah? You guys okay? I think so too. Let's go on. It is in your book if you guys need to refresh any of the operations, what's legal, what's not. I don't think we need to memorize them or write them down. Aha! Let's talk about it. Unit vector. Unit vector. Don't worry about the I's and J's right now, but do put your arrow notation on top of that vector V. What's going on, kiddo? Do you need them? All right. I do get a little baby workout. Unit vectors, unit circle, length of 1. Unit vectors, unit circle, length of 1. This isn't the unit circle. I'm just relating the two because unit circle had a radius of 1. Unit vectors have a length of 1. I'm going to actually move this little v down because he's actually our example that we're going to solve in just a second. Let me show you the formula first to get a unit vector. You want to take vector v, finding a unit vector with the same direction as a given vector. We'll say v. Okay. The unit vector of v is equal to, if they give me a vector with components, if not, I'll have to find the components. But if they give me a vector with components, let me put that in parentheses up here so you know exactly what you're using. It's just a formula. Just a formula. It's no big deal. If they give me a vector v with components a and b, all I need to do is take a and divide him by the magnitude of v. I'm scaling him back, and take b and divide him by the magnitude of v. I'm scaling him back. If you have a highlighter, remember how I said you can make a reference sheet for this test, yeah? If I were you, this would be one I would make sure to include, because it's really just a formula. If you're given a and b, if you're given components of a vector, all you got to do is scale it back. And how do you scale it back? You figure out whatever the length is of the vector now and say, oh, no, I can't have you, I need 1. So in this example, what did they give me as the components of vector v? 7 and 5. And you might not know it yet, but since they're asking you to find the unit vector, I'm kind of guessing it's not a unit vector to begin with. How could we prove that? We could find the magnitude and say, well, how long is he? Well, how long is he? Wouldn't we have to figure out the hypotenuse if we have over 7 and up 5? Oh, yeah. There's a formula for that. It's a formula you can memorize, or it's an idea you can understand. But either way, 7 squared plus 5 squared, isn't that going to be 49, 25, 60, 74? Yeah. Mental mathers, you actually got there, not just agreeing with me? It's dangerous just to agree with anyone, especially authority. Respect them, but don't necessarily immediately agree with them. Try to learn from them. Us. But you don't necessarily have to agree right away. I'm just going to take that and then divide. What do you guys think about with the back of the book? Sometimes you have to read your audience. Sometimes you have to think ahead to be like, I think I know what the book would do. It would get rid of, not 74, but square root. Good, Joe. It doesn't, remember? We don't leave square roots down there. So this is the formula, and you are totally right. And some of you could probably make that match in a multiple choice question as long as you remembered how rationalizing works, yeah? You would need to multiply top and bottoms by the square root. Unless a perfect square goes in. It's not a perfect square. 2 goes in 37 times. Both of those are prime numbers. Nope. 7 root 74 over 74. And then 5 root 74. Would be the final answer. But do you guys see how the formula, all we had to do was plug it in? And this is what we call the unit vector of v. So technically it's not v equals 7, 5. This is actually the unit vector of v. The little subscript is just telling us who it's of. So our final answer would be all nice and pretty and rationalized. But the current length is, well, root 74. Any mental mathers out there? Isn't that somewhere between 8 and 9? Between 64 and 81? 8 point something, something, something. Not 1. So how do I make it 1? How do I make it a unit? Divide. You guys highlighted that formula, right? I saw a lot of you guys getting your highlighters out. Yes. Nice. Keep thinking of that reference page. But pause. Just a few of you might be getting lazy because you're like, psh, we have a reference page. Do you still need understanding to know how to apply a reference page? Yeah, the AP Physics exam gives you this huge old list of formulas. And it's still one of the hardest APs to pass. Just having the formulas isn't enough. You have to understand. Okay, speaking of unit vectors, little guys with a length of 1, there are actually 2 little special guys. We give special names to 2 unit vectors. We give special names to, I put little arrows above just because we can't do bold, remember? I is the unit vector 1, 0, just going right 1 and that's it. And j is the special unit vector 0, 1. You can actually call I the special horizontal unit vector, and you can call j the special vertical unit vector. I'm building up to something. Hold on. Right now you're like, why are you throwing letters at us? Well, let me label them in a graph really quickly. I is this guy, going right 1 and up 0. J is this guy, going up 1 but over 0. I should say up over 0, up 1 is a better way of putting it. They're just special guys with special names, but they're also actually used for a special notation. We've talked about components. Components have the little side brackets. But components look an awful lot like points, and so some people confuse them. And it doesn't really, like the side carets, have no meaning as far as vectors. So there's another way of writing vectors. Without just giving a picture and saying 0, 0 to 7, 5, hey, look, it's a vector. Without just doing the side carets and saying, oh, it's the vector 7, 5. There's one more way of writing it, and the other way of writing it is called a linear combination. But the nice thing is, the meaning really isn't that different. It's just a little bit snazzier, a little bit more technical. So if we were talking about that vector w, there's his picture. He's going from 0, 0 to 4, negative 5. He's going right 4, down 5. Even though he can move around, he's always going right 4, down 5. We could put it in components, quick review, which would just be right 4, down 5. No big deal. But a lot of people would confuse that and not necessarily know what you mean. And so they technically have this other notation that means the same thing. It's just written a little bit differently with i's and j's. Because I is the right-left vector and j is the up-down vector. And so if we multiply I by like 4, all of a sudden we're going over 4 of the i's, which is going over 4 units. And then if we move or go negative 5j, we're going 5 times j, but in the negative direction. It'll get us there the same way as the components do, just the meaning is a little bit richer, a little bit deeper. P.S. Putting little vector arrows above everybody. Above everybody, above everybody, above everybody. I understand the struggle in your homework, which is why I'm going and doing them above all of my little nice bold letters that I was able to type. Okay. So down here, what if they give you vectors in a different notation? What are you going to do? Same thing you did before. Instead of just putting them in side carets, you're going to add little i's and j's to keep them in the same form. Priscilla, what's up, kid? Just me showing W. Not usually X or Y because it's used so much elsewhere in math. But remember, vectors are just little lowercase letters, whatever they are. Yeah. We don't usually go, I don't think you'll see any vectors like A and B because we're using that for like the components. X and Y gets used everywhere else. I, you wouldn't think it's used, but he does. But yeah, you could technically be any lowercase. We're going to be using U's and V's and W's. That's probably about it. Yeah. Yeah, I and J, they're actually defined to be the horizontal vertical vectors. So even though we can change the names to be U, V, W, X, Y, Z technically. Of I and J alone, yes. Yes. But, Joe, that's why we're multiplying by 4 and negative 5 to get 1 times 4, the length of 4, and then 1 times negative 5, the length of 5. Does that make sense? Kind of. Has anybody already gone for it?
Yeah.
2V, don't you just need to take V's components? But they're I's and J's. That's okay. That's just going to be instead of 3i, 6i. And instead of negative 2j.
Negative 4j.
Yeah. You get to do the same easy math. It's just you're not putting them inside carets with a comma. You're putting i's and j's with them. Could you write it in components? Definitely. What would this be in components? 6 negative 4. They mean the same thing. Just two different forms. So I want you to see it both ways and understand both ways. Jason?
So in like a long answer on a test, if you wrote with the i's and j's, you'd be fine?
Yeah.
Okay, cool.
Totally fine. I's and j's or side either one. But if I said the wording linear combination versus components, it'd be on your reference page, hopefully. But that would point you to a certain direction. How about
4i plus
good?
3j.
4i, just because that's under I, right? Plus 3i. We're still just combining the x's and the y's. It's just maybe even a little bit easier because you can actually see the like terms that combine, right? Sorry, 5 minus 2j was positive. Would that be in components if you were allowed to write it in that? But a lot of people see components and just think of like a point at a certain location instead of realizing its motion and movement through different steps. So I don't know. Both notations are good. Linear combination is just a little bit richer. So if you guys are highlighting, you could just maybe do an example on this one, but linear combination is specific wording when dealing with putting a vector with i's and j's. Means the same thing as components. So what if they say something like find the unit vector? Uh-oh, got to practice what we just talked about. What do you guys think? What did the formula say for unit vectors? Divided, but we have to start with what we have, right? So what do we have for u right now? 1i. So we're going to have 1 over times I. And then we have plus 5 times j, right? Who do I need to divide by? The magnitude. So let's come over here and do, how do we do magnitude when we have linear combinations? Square root, good, but don't worry about the i's and j's, just take the 1 and 5, good. Just take your a, which is your 1, take your coefficients. So if it helps, some of you might want to actually, if you're given a linear combination, think about it as a component. Like if you get used to components, you can take a linear combination and rewrite it and then go to your formulas. Or get used to reading linear combinations and pulling out the important information. But whether you're doing the components with 1 over and 5 over or the linear combination with 1 over and 5 over with i's and j's, you still just have to divide by, who's this guy? Square root of 26, right? So you can go to components first and then come back to linear combination or go straight to linear combination. But you guys know the back of the book would rationalize, right? Multiple choice answers on a test in proper form would rationalize. But the nice thing is, remember, if it's a matching question, you just have to make it match. Unit vector. Got him. Written in components or written in linear combination means the same thing. What you thinking? It's okay? Okay. Some good pondering. Brains are working today. Wait a minute, but what is this page? How to get direction and how to get magnitude. Haven't we already kind of talked about it, even though we didn't make it super official and highlight stuff? Didn't we say for any vector, whether it's i's and j's or whether it's components, didn't we already say what to do? I've been showing you guys a's and b's all along because I think it's easier. I've been trying to show you triangles all along so that it's not brand new on this page. This is our page of basically just summarizing and saying, okay, so what do we do if we have a's and b's, whether it's here or whether it's here? We already know magnitude. That's review. Square root of a squared plus b squared. We've talked about him a lot. And angle, we've done him even though we didn't talk about him. Because for the angle, all we have to think about is tangent. Because tangent says tangent of theta is equal to opposite over adjacent. So if they give us magnitude and direction, we can actually find our components another way. Well, wait a minute. But if we don't have A or B, we're going to get kind of lost in that one. Okay, we can find theta using tangent inverse. And there's going to be some warnings with that. So if you guys remember, tangent inverse only puts us in certain quadrants, and maybe we're in a different quadrant. So we're going to have to check the picture. Yeah, we have to check the picture to make sure that we are getting in the right quadrant with our calculator. Otherwise, we might have to like add 180 or add 360. So we might have to do a little bit of work on the thetas. So hold on, wait a minute. Tangent only helps if I have A and B in getting theta. Who else could be helpful? Well, we have sine. Sine equals opposite over hypotenuse. Cosine equals adjacent over hypotenuse. This one says, what if you're given magnitude and direction? I could just put DIR, right? Magnitude and direction. And this one says, what if you're given components or linear combinations? So this is our little converting page, how to convert from one to the other. If we're given magnitude and direction, we're going to actually use sine and cosine. And we're going to say, hey, we can get A and we can get B using magnitude with, well, A is adjacent, so cosine. B is magnitude using, B is opposite, so sine. We're actually taking these little trig ratios and using them. But the nice thing is you guys don't have to reinvent the wheel and make up the formulas every single time. You actually just get to use them. So when you're converting, maybe include that check the picture. You might want to get an example of that on your formula card. But long story short, if we're converting, these are the formulas you're going to be using. We just saw a second ago, if you're adding u plus v, the picture is so much harder than just having components. But what if they don't give you components? What if they're Despicable Me, the little criminal dude, and they don't know that there's things called components? All they know is magnitude and direction. Okay, fine. I'll plug it in and I'll get A and B. But what if they know there are components, but the problem is asking you for magnitude and direction? Well, then we have to go ahead and translate our information one direction or another. So this is the nice, huge, big conversion page of how to go from Despicable Me's magnitude direction to what we really want, which are components, because stuff's so much easier with them. Adding, subtracting, multiplying, I love it with those. Or if we have components and we need to state our information with magnitude and direction, we're going to be using our other formulas. So if you guys want, we could even technically, even though we've already talked about them, we could throw this guy, I guess, down here. Because if you're given A and B and you're getting magnitude and direction, I guess that's a good way of putting it. And grouping it for your reference card. It's a little bit nicer. Now it's awkwardly tall. Anyway, do you guys get highlighted the important information at least? I don't think homework really says to convert. That's not really a word that we use with vectors, but that's ultimately what's going on, converting the different forms. Now, where are we at? Finding components from magnitude and direction angles. Oh, hey, we have formulas. Finding components when you add magnitude and direction angles. Oh, hey, if they give us more than one and tell us to add, do you think we need to find his components and then add them together? Yeah. Got it. So, man, we're up in the 70s already. Ooh. What have we not gotten to? Word problems. But you know the nice thing is, I said something would still be due in Google Classroom tomorrow, right? Guess what that something is? Homework. Where do the word problems and application problems start? The 80s? Okay. I'll say up to the 80s. You guys do not need to go into the 80s at all. Sound good? So homework for the Google Classroom. I'll try to put a note in. I'll try to do it. I don't know if I can do it during nutrition. I have to run and do an errand. But I'll try to put a note in. But you guys